We all look up at the night sky and wonder, where did all this come from? How did it all begin? For centuries, we thought the universe was eternal and unchanging, a static backdrop to our lives. But then, we discovered the universe had a beginning, the Big Bang. About 13.8 billion years ago, everything, space, time, matter, was compressed into a single, unimaginably hot and dense point. The atoms in our bodies were forged in stars, which themselves were born from the aftermath of the Big Bang. So when we talk about the universe's beginning, we're also talking about our own. Science lets us rewind the cosmic clock, tracing the expansion of the universe back to a time when everything was smaller than an atom. But, as we approach that first instant, our understanding falters. Physics predicts a singularity, a point of infinite density and temperature. This suggests our story is incomplete. The Big Bang may not be the absolute beginning, but the start of the chapter we can read, which leads to a deeper question. If the Big Bang was the start, what, if anything, came before? Our journey begins at the edge of the known cosmos. The Big Bang wasn't an explosion in space, it was the expansion of space itself. There was no center, no single point of origin, every point in the universe began to stretch all at once. Imagine raisin bread rising. As the dough expands, all raisins move apart. That's what galaxies do. In the 1920s, Edwin Hubble discovered that distant galaxies are moving away from us, the hallmark of an expanding universe. But we're not at the center. Every observer, anywhere, would see the same thing. Space itself is expanding, carrying galaxies along. If we run the clock backward, all of space contracts, density and temperature rise everywhere. The Big Bang singularity isn't a place, but a moment in time when the universe's density was infinite. It marks the beginning of time as we know it. If the Big Bang was the start of space and time, asking what came before is like asking what's north of the North Pole. The concept may not make sense within our current framework. We're trying to peer beyond the boundary of our own reality. It's a challenge that pushes the limits of our imagination and science. To understand what came before, we must rethink the very nature of existence. Asking what happened before the Big Bang is a profound challenge. Einstein's general relativity tells us space and time are woven together as space-time. The theory works beautifully until we reach the universe's beginning. Rewinding the expansion, relativity predicts a singularity, see infinite curvature, infinite density. According to the math, this is the beginning of space-time itself, no before. But many physicists see a singularity as a sign the theory is incomplete. In science, such breakdowns have led to new theories, like quantum mechanics. The Big Bang singularity may be a clue pointing to a deeper theory, quantum gravity. Quantum gravity would unite relativity with quantum rules, describing space-time at the smallest scales. It could resolve the singularity and reveal what happened at, or even before, the Big Bang. The search for this missing piece is one of the greatest quests in physics. It could finally give meaning to the question of what came before. One of the strongest pieces of evidence for the Big Bang is the cosmic microwave background, or CMB, a faint glow of microwave radiation filling the sky. Discovered in 1965 by Arno Penzias and Robert Wilson, it's the afterglow of the Big Bang itself. For 380,000 years after the Big Bang, the universe was a hot, dense soup. Light was trapped in a cosmic fog. As the universe expanded and cooled, atoms formed, and light was freed, traveling across the cosmos ever since. This ancient light has been stretched by the universe's expansion, now appearing as microwaves. The CMB is a snapshot of the universe as a baby, a stunning confirmation of the Big Bang. It's almost perfectly uniform, but satellites like COBE, WMAP, and Planck have revealed tiny temperature fluctuations. These tiny ripples, just 1 part in 100,000, are the seeds of all cosmic structure. They grew, under gravity, into the galaxies and clusters we see today. The CMB lets us look back to the very edge of the visible universe. It's a direct window into our cosmic origins, and it may hold clues to what came before. Could the CMB contain hints of an earlier universe? Some scientists think so. The CMB shows strange anomalies, like a large cold spot and unusual alignments. Physicist Roger Penrose's conformal cyclic cosmology suggests our universe is one in an endless series of cycles, or aeons. In this model, each aeon begins with a Big Bang and ends in a cold, empty void, which becomes the next Big Bang. Penrose claims that collisions of black holes in a previous aeon could leave faint circular patterns, Hawking points, in our CMB. Most scientists are skeptical, but the search for such evidence is ongoing. If true, it would mean the Big Bang wasn't a perfect reset, but a bridge between cosmic cycles. The idea of endless cycles is ancient, but modern physics gives it new life. Loop quantum cosmology, a theory of quantum gravity, suggests spacetime is made of tiny loops. There's a smallest unit of space. This means space can't be compressed to a point. The singularity disappears. As the universe contracts, density rises but never becomes infinite. At maximum density, gravity becomes repulsive, causing a bounce instead of a collapse. Our Big Bang could be the rebound from a previous universe's collapse. A big bounce. This model solves the singularity problem and suggests an eternal, self-renewing cosmos. Each cycle could have different properties, or inherit traits from the last. While unproven, it's a mathematically consistent and philosophically satisfying alternative. Another radical idea comes from cosmic inflation. Inflation proposes that in the first instant after the Big Bang, the universe expanded exponentially. This explains the universe's uniformity and flatness. But many models predict inflation never completely stops. Eternal inflation. Our universe is just one bubble in a vast multiverse, each bubble a separate universe with its own Big Bang. The Big Bang, then, is just the start of our pocket of reality. Other universes could have different laws of physics, or even dimensions. We can't see or reach them, but some believe collisions between universes could leave marks, like circular patterns, in our CMB. The search for such evidence continues, whether or not we find it. The multiverse idea expands our view of what before the Big Bang could mean. Quantum mechanics offers another perspective on the universe's origin. At the quantum level, particles can pop in and out of existence, even in a vacuum. Some physicists propose the universe itself is a quantum fluctuation from nothing. Here, nothing means no space, time, or matter, just quantum potential. A fluctuation could create a tiny speck of spacetime, which inflation then expands to cosmic size. The total energy of the universe could be zero, balancing matter and gravity. In this view, the universe is self-contained, needing no external cause. Time itself may have emerged with the universe. Before that, before has no meaning. The Big Bang is the moment this fluctuation occurred. It's a radical, self-sufficient origin story. So, where does this leave us? We have several bold ideas: endless cycles, a multiverse, or a quantum fluctuation from nothing, all challenge the notion of a single, absolute beginning. The Big Bang may be just our chapter in a much grander, possibly eternal cosmic story. We are the universe's way of thinking about itself, the product of a 13.8 billion year process. Our curiosity connects us to the Big Bang and whatever came before. The universe continues to expand.